Okay, so we're going to be doing a bunch of Laplace transforms today. Here at the bottom of the Canvas course, I have a Laplace table, and there are other. You can literally just Google a Laplace table and find one. Here's another one that has a whole page. It's not laid out as pretty, but it does have like the definition on it. This one is missing. It doesn't have the definition. Maybe a little fuller. It might have a little more stuff in here. It definitely has the linearity rules and a couple of examples. And then the derivatives, I think, are a little bit clearer here. So we're just going to do a bunch of examples of Laplace transforms. That's our goal today. Okay, so we're going to start with using the definition of the Laplace transform. So we're doing an integral here. We're not using a table. We're not looking anything up. You're going to have a question just like this on your test. And I went ahead and looked up what the answer is ahead of time. This is what we're going to get. We're going to use the definition of the Laplace transform, which is the, oh, whoa, undo that. The Laplace transform. Why is it still thick like that? Oh, maybe that size. Let's try that. Okay, the Laplace transform of some function f is the integral from 0 to infinity f of t e to the negative st dt. We're going to integrate out all of the t's. T is our variable of integration. Still a little thick, but thinner. T's our variable of integration. It's going to disappear. In this case, like we could use x or t. I'm just going to use t. So I'm going to think of this function as a function of t. But that's going to get integrated out. Our final answer is only going to have s's in it. We can see that here. Okay, so in this case, f of t, let's write that in terms of t, is this piecewise defined function t between 0 and 2. The equal to's don't matter. If this one had the equal instead of that one, it wouldn't change anything because the integral of a point is 0. And then 2 for t greater than 2. Okay, then that means we're really just going to split up this integral then. The integral from 0 to infinity of f of t e to the negative st dt. We'll just split it up over these different domains. We're going to use from 0 to 2, we're going to use this formula, t e to the negative st dt, plus, and then from 2 to infinity, we're going to use this formula, to e to the negative st dt. We can't look either of these up in a Laplace transform table. If I go to my tables, any of these here, all of these are using the definition, the integral from 0 to infinity. This is for the entire thing. This is the Laplace transform of f of x equals t on 0 to infinity. The table doesn't do me any good, is what I'm saying. I have to actually calculate these integrals. This is a calculus problem. Here, I'm going to have to use integration by parts. This one I can just do. So let's label these 1 and 2. And 2 is much easier. Let's go ahead and do him first. The antiderivative of e to the negative st dt. If I integrate that, I'm going to pick up a negative 1 over s. And I'm going to evaluate that from 2 to infinity. So basically, I did a integration by substitution there. U is negative st, du is negative s. I did all that in my head. And the easy way to think about that is if I took the derivative of this, e to the negative st dt, I would pick up a negative s on top. Since I'm doing antiderivative, I get the negative s on the bottom instead. Okay, now technically this is a limit here. I really should, if I want to be very particular, I should be writing this integral as a limit. This is an improper integral. So this is really limit as b goes to infinity of integral 2 to b. But we've done enough of those. We can skip that. We can kind of hand wave this part and say that this is -1 over s e to the negative infinity, when we really know that's a limit, minus, oh, I should bring my 2 out also. I'm bringing this 2 out. E to the, what do we get? Negative 2s. Remember, these are t equals, and t goes to. My limits are t because my variable of integration is t. And again, like I've said this a few times, this is really supposed to be the limit as t goes to infinity or negative infinity in this case. We know that goes to 0. So I've got this -2 over s out here times this other negative. I think we just get 2 over s e to the negative st, or negative 2s. Okay, that's just this part. Now we're going to do 1, and that's going to be an integration by parts. So I have the integral from 0 to 2 t e to the negative st dt. So I'm going to have my u and my du, my dv and my v. U is going to be t, du is going to be dt, dv is e to the negative st, and v will be -1 over s e to the negative st. Then just to remind you, antiderivative of u dv is uv minus integral v du. So then this integral here will be uv, so u times v, t times -1 over s e to the negative st, evaluated at my limits 0 to 2, minus antiderivative u dv, or v du, these two, -1 over s e to the negative st dt, and we're going from 0 to 2. That's an equal sign right there. I want to clean that up a little bit. Okay, so let's go ahead and evaluate that. We're going to be really careful with our signs here, especially since we're going to have 3 negatives coming out of this. I'm going to pick up another negative when I do that antiderivative. I've already got 2 negatives. And then when I plug in my limits, I'm going to have top minus bottom. We get negatives all over the place. Excuse me. That's where these problems go wrong. And heck, there's a good chance I'll mess up a negative and we'll have to go back and find it. So you just got to be really careful with your signs here. So let's do this guy here. Plug in top minus bottom. Remember, these are t equals. So plugging in t equals 2, I get -2 over s e to the negative st. Then when I plug in 0, the whole thing becomes 0. So -0. These negatives here cancel, and so I'm just going to do that. I'm going to go ahead and do this integral. So the antiderivative, we've done this twice now, e to the negative st dt, I pick up a -1 over s, but I already had an s.
I have a question.
Yeah.
The negative st on the first part, won't there be -2s where the exponent is?
Thank you. Thank you. We should not have any t's left over at the end. I'm plugging in 2 for t. So negative 2s. Thank you. Okay, and then here, so antiderivative e to the negative st, I pick up a negative 1 over s out front times this positive 1 over s. There's my negative s squared e to the negative st evaluated from 0 to 2. So here I've got, I'm just going to write all this out, negative 2 over s e to the negative 2s, plugging in a 2 for t. These are t equals. I'm going to keep writing this. Plugging in a 2, I'm going to get a minus 1 over s squared e to the negative 2s. Plugging in a 0, this becomes 1. Remember, it's top minus bottom. So I'm going to have a minus times in that minus. I'm going to have a plus 1 over s squared. E to the 0 is 1. Okay, so now I got to put all this together. So I've got 1 plus 2. I got a negative 1 over s squared e to the negative 2s. I got a 1 over s squared. Oh, wait, where did I get this? Okay, I left off a term. I got 3 terms here. I have a negative 2 over s e to the negative 2s minus a 1 over s squared e to the negative 2s. I got a plus 1 over s squared. And then plus this guy here, plus a 2 over s e to the negative 2s. That's an s. These two happen to cancel out. That's not going to happen every time. There's nothing special that made that happen. It really just is coincidence. A lot of these you end up with 3 terms or 4 terms. So I don't want you to get the idea something's always going to cancel out, but it did here. And then if I factor out that 1 over s squared, I'm going to have a 1 minus e to the negative 2s. That's an s. My s's don't look like s's here. Is that what we were supposed to get? Yes, it was. So a lot of places you can make a silly mistake. Here, you got to be very careful with these. Okay, so that's using the definition. And like on your actual test, test 3, it's coming up soon. You're going to be asked to do that with the piecewise function. It's going to be a lot like this problem. The rest of these, we're not using the definition. We're going to be using the table. So these are just kind of plug and chug. These are find the formula that matches what you're looking for in the table and just apply the formula. So I've got f of x is x to the 7th. So I'm going to look at my table and I'll use the one that's in the Canvas page. So that would be here. So t to the n. I kind of want to look at this and think of that as f of t is t to the 7th. So we're using this formula right here. It says on top, we're going to have n factorial. On the bottom, we'll have s to the n plus 1. So the Laplace transform of t to the 7th will be the exponent factorial over s, and then the exponent goes up by 1. Remember, with Laplace transforms, you're changing from the time domain to the frequency domain. We're changing from t to s. On one side, we have all t's or x's, as the case may be. On the other, we have all S's. So here, I'll write this guy in terms of t. So I want to find something in my Laplace transform table that looks like this. E raised to something times sine of something. So these aren't going to do it. Oh, here now we're looking good. Here's something. The Laplace transform of e to the at sine of kt looks like this. And that's what I've got. There's my a is -1 and my k is 2. So I'm supposed to get k over s minus a squared plus k squared. Let me make sure I wrote that right. Now it should have been a k on top. So that's my a is the number beside t, and that's my k. So it's really just plug and chug. We're going to get 2 over s minus -1, s plus 1 squared plus, and just to make sure this is clear, that's a k squared 4. Most of the time when we're doing Laplace transforms, the hard part is going backwards. It's going from something that looks more like this to coming backwards and doing the inverse Laplace transform. But going forward is good practice for learning about going backwards. Okay, here we've got this sum of functions. The Laplace transform is a linear operator, meaning you can distribute over addition and you can pull constants out. So the Laplace transform of t cubed plus 3 cosine of 2t is the Laplace transform of t cubed plus 3 times the Laplace transform cosine 2t. It's a linear operator. So I can just distribute. I can pull that 3 out front. Okay, I already know how to do this guy. T raised to power, we get the old power on top factorial, so 3 factorial, divided by the old power plus 1, s raised to the old power plus 1. Okay, we're going to have to look up cosine of 2t. So here we have cosine of kt. We get s over s squared plus k squared. Notice the difference between sine and cosine. For sines, you just have a number on top. For cosine, you have your variable, an s on top. We want this one. So that's going to be s over s squared plus k squared. And k here is 2. So I get an s over s squared plus 4. That would be that guy's Laplace transform. Okay, now let's go backwards. So now we're doing inverse Laplace transforms. Now I'm looking over here on this side and trying to work backwards. So I have 1 over s squared. I want something raised to a power. We're doing this one, but backwards. So going forward with t raised to a power, those are just kind of easy. It's a lot kind of like the power rule for integrals, right? We end up with this plus 1 as our power. I mean, things get flipped over and we get this factorial. So it's obviously it's a different formula. But going backwards, we got to figure out who's playing the role of n here. I have s squared. So n is 1. I want to look at this as 1 plus 1 because that's my n. So now I have to think of this as I need the Laplace transform of t to the n is n factorial over s to the n plus 1. I need to make sure I have an n factorial on top. In this case, I do. 1 factorial is just 1, so that is 1 factorial. If it wasn't there, I would have to put it in. But in this case, 1 factorial is just 1. So now we're just working backwards. N is 1, so this is just t. So the Laplace transform of 1 over s squared is just t to the first. The inverse Laplace transform. This is the same problem. The inverse Laplace transform is also linear. That too I can just bring out. The inverse Laplace transform of 2 over s squared is just twice inverse Laplace transform of 1 over s squared. So the 2 just comes along further right. This would be 2t. Okay, now we're going to have to start doing a little more work. You're not going to find anything in the table that fits that perfectly. The closest I have is this guy right here, 1 over s minus a. I've got a 2s minus 3. I got to get rid of that 2. So this is what I'm thinking is the Laplace transform of e to the at is 1 over s minus a. I have to make this look like this. So I got to get rid of that 2. I don't know if I gave myself enough room on this one. By factoring that 2 out, that 1/2, so that would give me 1 over s minus 3/2. So I pulled a 2 out from the bottom. Now it looks like this. A is 1/2. So the inverse Laplace transform of what I have here the 1/2 just comes along for the ride because this is a linear operator. And I get e to the 3/2 t. A is positive 3/2. There's a minus built into the formula. Okay. Now you might look at this one and think, oh, that's a lot like that one. It's just something raised to a power. Kind of. It is something raised to a power, but it's this linear term, s minus 2 raised to a power. So I need to find something. See, this won't do it. That's not raised to a power. This won't do it. I need something, oh, maybe like this. Look at that. That'll do it. 1 over s minus a squared. Oh, I have cubed. Oh, yeah, that was close. Oh, this one might do it. See, that was only squared. I've got cubed. So for this to be cubed, my little n there must be 2. All right, so let's write this one down. I really don't know if I gave myself enough room on this one. The Laplace transform of t to the n e to the at is n factorial over s minus a to the n. Let me check and make sure that's right. N plus 1. Sorry, I'm trying to write a plus 1 here, and it's right at the edge. I don't want to go off the screen. Okay, so A is 2. That part's easy. N is also 2, because 2 plus 1 is 3. Problem is, I don't have an n factorial on top right here. So I need to make this thing 1 over s minus 2 cubed. I need to write that with a 2 factorial on top in order to fit this form. But now I've just made stuff up. I just put a 2 on top. I can't just make stuff up. I need to also cancel that out. The Laplace transform is linear, so this 1/2 now is going to come along for the ride. So when I do the inverse Laplace transform, of stuff, I don't have space to write it, I'm going to get a 1/2 t to the n e to the at. So all of these are about hammering what you have into a form that fits the table perfectly, and then just applying the table. Okay, all of them so far have been pretty easy. The reason I'm spending so much time on them is we have some complicated ones coming up. Okay, this one, I'm looking for something that's got a number, not an S. Look at that guy. He's got an S on top. This one doesn't. Got a something plus or minus something squared and then plus a number. I'm looking for this form over on this side. Okay, that's looking like maybe one of these over here. Okay, notice the difference here. There I've got pluses, here I've got minuses. I've got a number on top, so it's got to be one either sine or sinh. I don't remember. I'll have to go back and look and see if I had a plus or a minus on the bottom.
It would be the sign.
Yeah. It's a plus. So that's this formula right here. K is 2 if I have a 4 right there. Oh, man, see, I got to be careful here. Oh, I don't. See, that formula, whatever is here, is supposed to be here squared. That should be 2 and 4. It's not. That's not my K. I got to look at this guy first and go, well, that's 3 squared. So I wish I had a 3 on top. Well, I can put a 3 on top. I can bring that 2 over, put a 3 on top, as long as I put a 3 in the bottom to cancel it out. Now we fit the form. Here's my K in K squared. Here's my A. We fit the form exactly. Then our inverse Laplace transform is e to the at. So there's A, there's K. E to the at sine of kt. So you got to massage these a little bit to make them look like the form you want. This one. Now I've got an S on top. Oh, but I don't have this minus A. Oh, man, look, even see here, I've got an S on the bottom, or on the top, but the bottom doesn't look right. I've got this S plus 1 squared plus 5. I've got an S on top. The formula says then, if I'm going to use this formula, if I've got an S plus 1 squared, I need an S plus 1 on top. I need to somehow get a plus 1 in there. So I have to take this guy and rewrite it as S plus 1 minus 1. Then split up that into 2 separate fractions, S plus 1 over S plus 1 squared plus 5 minus 1 over S plus 1 squared plus 5. Both of these look like what I have in the table. This is the cosine one. This looks like a sine one. Oh, but I got to play the same game I just played on this one. My K here, excuse me, is square root of 5. That's square root of 5 squared. So k is root 5. I'm supposed to have a k on top in this formula. If I got a k squared there, I have to have a k here. So I got to put it in myself. I have to go, oh, well, I'm going to throw in a root 5 there, and I can fix that by putting a 1 over root 5 here. Then this fits the cosine form. This fits the sine form. We will get e to the negative t cosine root 5t minus 1 over root 5 sine root 5t. Now, would you have thought to do that if I just handed you this? Would you have thought to add and subtract 1? Probably not. That's why I'm doing these problems. Now you should think to do that. Okay, we're going to have to play similar games with these. These, we're going to have to go through an extra step to turn it into something that looks like that, and then play this kind of game here. And like this one's going to be really complicated, so I went ahead and wrote down what the answer is going to be. Okay, so if this factored, it would be easy. If it factors, you just factor it, use partial fraction decomposition, and you get two different exponentials. Like those are all the same. Anytime you have a quadratic that factors, you factor it, use partial fraction decomposition, and you get two different exponentials. This doesn't factor. I'm going to have to use completing the square in the bottom. I have to turn this into something that looks like these two. And you just know that by looking at it and seeing it doesn't factor. So there's going to be a lot of steps here. In fact, did I leave? Well, I hope I left enough of them. So I'm going to rewrite this guy in the bottom like this. Forget about that 2 for a minute. He's just going to hang out. Half of this guy, half of b is 1, squared is 1. So I'm going to add 1 in the bottom, but I can't make up stuff, so I'm also going to subtract it out. I could have also said I'm going to split that 2 up into 1 plus 1. It's the same result. I don't want the parentheses yet. So that'll be s squared minus 2s plus 1 plus another 1. So that 2 became 1 plus 1. This is a perfect square trinomial. I know because I completed the square. That is s minus 1 squared plus 1. Now it fits the form. Now it looks like the sine one. There's no s on top. My k is 1. I got a 1 squared there. I've got a 1 there. My a is also 1. So I'm going to get e to the t sine t. For the inverse Laplace transform. The inverse transform of stuff up there is e to the t sine of 1 t. This one's going to be a lot more work. I hope I left enough room for it. Okay, we're going to play the same game in the bottom. S squared plus 2s. Half of 2 is 1. 1 squared is 1. So plus 1 minus 1 plus 5. Or if you like, think of it as breaking off 1 from this 5. Because negative 1 plus 5 is 4, right? So you could think of it as I'm going to write 5 as 1 plus 4. So I get this, s plus 3 over s squared plus 2s plus 1 plus 4. That's a perfect square trinomial. That'll factor s plus 1 squared plus 4. Okay, I'm pretty happy. This kind of looks like this formula here with the cosine. I've got the bottom looking how I want. My A is a -1, I think. Yeah, that's S minus -1. My K is 2. Problem is these are supposed to match. That should say S plus 1 there instead of S plus 3. So we got to go through whatever steps we have to make that look like that. So the easiest way, the way I would approach this, there are dozens of ways to do this. I would break off the ones I don't need. I would split this up and go, well, that's a +1 plus 2 more. Now this is going to give me an exponential times a cosine. This will be an exponential times a sine. Sometimes you get here, you do this math, and now you got to multiply and divide to make things work out. Like maybe these numbers won't match up right. So you got to play the same kind of game we did here and go, oh, I was supposed to have a √5 on top. So let me multiply and divide it in. This one worked out nicely. Like whoever wrote this problem, I guess did it on purpose. See how we've got our K squared here and our K. That fits this formula perfect. And on top, we've got the S minus A and the S minus A squared. Everything worked out perfect. We're going to get one of these and one of those. Usually that doesn't happen and you still got to do a little more finessing. This will be e to the negative t cosine of 2t. This will be e to the negative t sine of 2t. Which is exactly what the back of the book had. Okay, stop the recording.